So first I'll solve a question from this unit 6 and then explanation of unit 5 topics. Alternate weeks I'm explaining topic, 1 week unit 4, another week, next week unit 5. A student set up a cell in attempt to investigate whether the potassium manganate is a strong oxidizing agent and then potassium dichromate. So student use potassium dichromate solution and chromium 3 sulfate, another one potassium manganate 7 and manganese 2 sulfate. And a platinum wire is used. The concentration of each solution is 0.1. What compound must be added to both beaker to allow a redox reaction to occur? So redox reaction can occur easily in acidic condition. So what we should add an acid, or we can also mention sulfuric acid because they specifically ask the name of the compound. So we will mention sulfuric acid. As in acidic medium, redox reaction can easily happen or occur. What must be added to set up a complete cell? Name the item and any chemical which is needed. To make a complete circuit, what is missing here? The missing is a salt bridge. And what is usually a salt bridge? It's usually a filter paper which is soaked in potassium nitrate, like group 1 salt solution, so that it can make the complete circuit. So the missing part is a salt bridge, and what compound? It should be dipped in a solution of potassium nitrate or group 1 salt, as they are all soluble. So we should add the salt bridge. And what is actually a salt bridge? Salt bridge is actually a filter paper which is soaked in potassium nitrate or sodium nitrate. In part C1, the voltmeter shows that the right-hand cell contain a positive electrode. Use this information, deduce whether potassium manganate is an stronger oxidizing agent than potassium dichromate, and explain how you made your deduction. So as I mentioned, the voltmeter shows that the positive electrode, like the right-hand half cell, contain a positive electrode. So this one is representing a positive electrode and the other one is representing a negative electrode. And in a chemical cell, the electron transfer is always from negative terminal to the positive terminal. So direction of electron flow, because if right-hand side is positive, the left-hand side should be negative, and the direction of electron flow is from positive to negative. And it means this substance is losing electron, like because there's a loss of electron. As there's a loss of electron, substance is losing electron, these electron transfer to the other side. So if a substance is oxidizing agent itself, it is reduced, and reduction is a gain of electron, like it should gain electron. So from left to right is the movement of electron. So the side where we have KMnO4, potassium manganate is there, KMnO4, and this one is there, potassium dichromate K2 Cr2O7. That is a potassium dichromate. This is the formula of the compound. The movement of electron is from negative terminal to the positive terminal. So what it shows, the negative terminal always lose electron in a chemical cell, and the positive, like these electron as it travel, this will gain electron. So it means Mn7 will gain electron. So Mn7, when it gain electron, it will turn into Mn2 because manganese 2 take 5 electron and turn into Mn plus 2. And so this substance is a reduction, or it is acting like an oxidizing agent for a substance which reduction happen acting like an oxidizing agent. So potassium manganate gain electron. So potassium manganate is acting like an oxidizing agent, or it will be a stronger oxidizing agent. So first thing, whenever you have a chemical cell, the movement of electron is always from the negative electrode to the positive electrode. And the negative electrode, the solution in which we have a negative electrode, that ions are losing their electron or oxidation happen for them, or they are acting like a reducing agent. And for the other solution, the electrolyte, the electrons move, they gain electron, and that change is known as a reduction. And if it's a reduction, the substance is acting like an oxidizing agent. So Mn plus 7 reduction happens, so it is acting like an oxidizing agent. So that was a question itself that they asked. uh, the voltmeter use the information deduce whether potassium manganate is a stronger oxidizing agent than. So potassium manganate is a stronger oxidizing agent. How we identify? We'll mention the movement of electron is there from the negative to the positive. So potassium manganate or Mn7 ion gain electron and reduce, so acting like an oxidizing agent. Then write the half equation for reaction which occur on the right hand side half cell when a current flow. So as we know, Mn7 is changing into Mn2. So we just have to write the equation for reduction, or KMnO4 is there. It turned into Mn plus 2. So the ionic half equation which contain MnO4, manganate ion is there, and the charge is -1 because Mn is +7 and each oxygen is -2. So 4 will be -8, and it turned into Mn plus 2. Now to balance a redox equation that is there in AS, that how to balance a redox equation. If we want to balance oxygen, we add water molecule. So we add 4 water molecules on the other side, so oxygen is balanced. If we want to balance hydrogen, we add protons. So 4 multiplied by 2, 8. So we add 8 proton, the hydrogen is balanced. And to balance the charge, after balancing all the other elements, to balance the charge, we add electron. So here plus 8 and -1, so plus 7 charge is here, total, the net charge. And here we have plus 2. So we can add the electron to a side where the charge is greater. So it will reduce. So how many electrons we should add? Because we want to make it 2. So we'll add 5 electrons here. So the charge is also balanced. So this is a balanced redox equation for a conversion of Mn plus 7 in manganate, in which Mn is plus 7 turned into Mn plus 2. And the color change in the left hand half cell when a current flow. So here 7 is changing into 2. So if a reduction is happening on the one electrode, in this solution Mn7 which is purple, it turned into Mn2 which is colorless. So if the reduction is happening here, the oxidation should happen on the other side. Oxidation means loss of electron. So what should happen? The chromium plus 3 should turn into chromium plus 6 because it lose electron. So the charge will increase. And what are as the oxidation number change for them, the color will also change. So chromium is plus 3 is green in color, and chromium plus 6 is orange in color. So the color change, what will the color change here? Chromium, initially most of them will be chromium 3 and then it turn into chromium 6. Dichromate 6 means like chromium is plus 6. So this one is green in color and this one is orange. And if they ask the color change in right hand side, so it was plus 7 turned into plus 2. So initially it was purple and then turned into colorless. So the color change on the left hand side, it will be green to orange. What change other than keeping a temperature at 298 Kelvin? Because we want to make a standard condition. Standard condition, the temperature should be 298 Kelvin. The pressure should be 1 atm and the concentration of the solution should be 1 mole per dm. So what change other than keeping a temperature would need to make a standard? If we want to make a standard, we should have a concentration 1 mole per dm cube. So what we should have, we should make a solution. The concentration of the solution should be 1 mole per dm cube, or the pressure should be 1 atm. That is for standard electrode potential. So using a solution of concentration 1 moles per decimeter cube to make a standard. And in part F, the standard electrode potential of the right-hand side cell is measured to be 1.51 volts. The reduction potential for another system is given by this aqueous sodium peroxide. Aqueous sodium peroxide disulfate is a colorless solution containing S2 and O8. State all the observed color and any color changes that expect if the solution of sodium peroxide disulfate is added to potassium manganate solution. So on the right hand side, the electrode potential is 1.51. So the one which is a higher value, like if we are comparing the two cells, and what does it mean? Always the electrode potentials are given for reduction. Like Mn plus 7 was there, it was gaining 5 electron, or the balance equation which we write, it means MnO4 with a charge -1 turn into Mn plus 2, and 4 water molecules were there, 8 protons were there, and 5 electrons. Reduction electrode potential are always to gain electrons, so it is given 1.51 volts. That's on the right hand side. So whenever two electrode potentials are there, how you will identify which one oxidation happen and which one reduction happen? The one which is having a higher voltage, higher positive value, or even both of them might be negative, but the one which is a higher value, reduction happen. So for this one, reduction happen, and this one, oxidation happen. So for the one which reduction happen, the forward reaction will be there. But for which oxidation happen, then the backward reaction will occur. Like Mn plus 2 will turn into Mn plus 7. So the question is, if we add to potassium manganate solution, what we will observe, or what will be the color change? So initially, because Mn7 is there, so already, like, we have a mixture of Mn plus 7 and Mn plus 2, so and it will be oxidation happen. So mostly we'll have Mn plus 7, so it will remain purple. So this will be purple. Why it is purple? Because the equilibrium will shift it towards the side of oxidation part, the one which is having, whenever electrode potentials we compare the one which is having a higher value, reduction happen, the other one, oxidation will happen. If it is added to manganese 2 sulfate, like here, manganese, because it should remain purple, but for this one, what happened? If it is Mn plus 2 is there, if mostly we have Mn plus 2, Mn plus 2 is colorless. So Mn plus 2 is colorless, it will turn from colorless to purple. So this will remain purple. This will remain purple in color. But for manganese 2 sulfate, it will turn from colorless to, because that is colorless. And Mn7 will be produced, so it will turn from purple to, from colorless to purple, because manganese 2 ion is colorless and manganese 7 ion is purple. So when we add sodium oxide disulfate, it won't change it, because it will shift the equilibrium towards the Mn7, so it won't change the color. But for plus 2, it will turn into plus 7, so it will change from colorless to purple. In question 4, salicylic acid is original name of a compound which can be obtained by bark of willow tree. The systematic name is 2-hydroxybenzoic acid. Give a simple chemical test which is positive for 2-hydroxybenzoic acid but not for benzoic acid. Like 2-hydroxy means because second position we have OH group, and state the reagent you would use and expect the result for 2-hydroxybenzoic acid. So how we can distinguish between benzoic acid and 2-hydroxybenzoic acid? So this is simply a test to check the presence of OH group in attached with the benzene ring. Like this is a benzene ring. So how we can distinguish? We usually add aqueous bromine and it will decolorize. That is one of the tests. Or we can also add any carboxylic acid can be added and it will give a characteristic steamy fumes will be there or a fruity smell. But to distinguish, like example, if a compound is having a benzene ring, this is a benzene ring, alternative carbon double bonds attached with OH. So how to distinguish this compound with other benzene ring? When OH is attached, that compound is also known as a phenol. So how we can distinguish a phenol from benzene ring? We usually add Br2, aqueous bromine. It will turn from orange to colorless, and also white PPT is there if we add too much quantity. So here add bromine. It will turn colorless. Compound known as aspirin can be prepared by 2-hydroxybenzoic acid. So aspirin, which is used as painkiller, can be manufactured from this 2-hydroxybenzoic acid. So first we have a 2-hydroxybenzoic acid. Then this is anhydrous of ethanoic acid. When we mix with each other, it will turn into aspirin. First, the steps are transfer 2 gram of 2-hydroxybenzoic acid into a dry and a pear-shaped flask. Then add 4 cm cube of ethanoic and anhydrous of ethanoic acid and followed by 5 drops of concentrated phosphoric acid. Then fit the flask with a reflux condenser and heat it on a hot water bath for about 5 minutes. Then after allowing the reaction mixture to cool, add 2 cm cube water down in a condenser and this hydrolyze the excess of ethanoic anhydride. And when the vigorous reaction has ended, pour the mixture in 40 cm cube cold water in a 400 cm cube beaker in an ice bath. Solid aspirin will form because when we cool down the precipitation, like the crystals start to, solubility decreases as the temperature. So then recrystallization of the product using a distilled water and a dry it. The data is there. The density of ethanoic anhydride is 1.08. The molar mass of ethanoic anhydride is 102. The molar mass of 2-hydroxybenzoic acid is 138. And molar mass of aspirin is 108. These are the hazard symbol for ethanoic anhydride. What is the meaning of each symbol? So first thing, look, there is a small difference between combustion and oxidation. If it was an oxidation reaction, like if they say oxidation, so there will be O here. But because if a compound is flammable, it can catch fire. So this shows that it is flammable, can catch fire. And the second one, it is corrosive. So if a compound can catch fire, this will be the symbol, so flammable. And the other one is corrosive. Next is calculate the minimum mass in gram for ethanoic anhydride needed for 2 gram of ethanoic acid to react completely. So you have to use a ratio because we want the minimum mass of anhydride of ethanoic. Ethanoic molar mass is anhydride is this is a density, this is 102 and this one is 138, 2-hydroxybenzoic acid. So this is 132. As there are 1 moles only, so 132 and 102, the ratio of the mass. 138 and 102. So this will be 138 and this will be 102. That's a ratio of their masses. So if we have 2 grams of 2-hydroxyethanoic acid, then how much we need? Like if we have 2 grams of this will be X. We just cross multiply. So the X will be 102 times 2 divided by 138. And this will give us the mass of the anhydrous of ethanoic acid, which we need for this reaction. So it is about 1.48 grams. So we need 1.48 grams. And the next part, show by calculation that the ethanoic anhydride used in Chapman is in excess. Like we use more than enough. So how we can work out? We have the gram per centimeter. We have the density, and we already worked out the mass. So using that, we'll find the volume. And from volume, we can compare the volume which we get the answer and how much is used in the experiment. Or there is also another way to check, like you have in the question 4 cm cube of ethanoic anhydride is used. So using this 4 cm cube and using this one, the density, you can work out how much mass is used and compare this mass with how much mass is reacted. So both ways are acceptable. You can do by any way, as density is mass over volume. So in the question they mentioned we use 4 gram, or even like here when we work out the mass, that was coming out, the mass of anhydrous of ethanoic acid was 1.48 grams. And how much we use for a complete reaction, we use we use in excess of that, we use 2 grams, or which is, we use 4 cm cube. Yeah. So using this 4 cm cube, we'll first find the mass and then we'll compare with 1.48. And so 1 mark, so density is mass over volume. So mass is equals to density times volume. The density that was given in the beginning of the question, 1.08, and the volume was 4. So when we multiply, we'll get the total mass, which will come out 4.32 grams. So 4.32 gram is what we used. But for we work out that for a complete reaction, we need only 1.48 grams. So it shows like the one which reacted is 1.48 and we use 4.32. So it shows that anhydrous of ethanoic acid or ethanoic anhydride is in excess or more than enough for this reaction to happen or occur. Show by calculation that ethanoic anhydride used in that was this part. And then student obtained 1.7 grams of aspirin from 2 grams of 2-hydroxy benzoic acid. Calculate the percentage yield. Percentage yield is a practical value divided by theoretical into 100. So this is a practically we are getting 1.7. But we'll find theoretically. So we'll again take a ratio between the limiting reagent, which is a 2-hydroxy benzoic acid, and the aspirin. So 138 and 180. So ratio of the mass, if we have 138 grams of 2-hydroxy benzoic acid, we should get 180 grams of aspirin. And if we have 2 grams of 2-hydroxy benzoic acid, then how much aspirin should be there? X. So we cross multiply. So when we cross multiply, like example, it will be 2 into 180 divided by 138. So theory suggests we should get 2.6 grams, but practically we are getting a 1.7 only. So to get the percentage yield, the percentage yield is a practical value divided by theoretical into 100. So practical value is 1.70. Theory suggests we should get 2.60 and into 100. This will give us the percentage yield of this reaction, which is about 65%. So this is only giving us 65% of what we expect. And usually in a reaction in which we do recrystallization, not all the solute will be crystallized. Even when we carry out filtration, some of the solute or a solvent left on the filter paper. So these are some reasons why we never get 100% yield for the crystallization product. A student drew a diagram of the apparatus for a reflux process. The diagram is shown below. Identify two errors in the diagram and state how they should be corrected to make apparatus workable. Assume that the apparatus is suitably clamped. So clamping is done. That does not have any difference. So we have to identify uh, because it should be a reflux condenser. What are the mistakes here? First thing, this condenser, like there should be a sealed condenser should be there. Like it should not allow any vapors to escape. That is one of the, and the thermometer, we don't have to use a thermometer. Thermometer should not be there. Like what is the missing part here? Like the jacket, the water jacket is missing. That is one thing. The second thing, for a condenser, we don't have to measure a temperature of the vapors here because that does not make difference. So there should be a water jacket because it's not like if water is entering from here, so water will mix with the vapor and vapor will escape with the water. So this won't work. How it should be there? Like there should be a water jacket, like whenever a condenser is there. So there's an inner wall of a condenser and then outside there's a water jacket. So water does not mix with the content in the flask. With this setup, the water vapors will mix with the content in the flask, so it won't work. Second thing, we don't place a thermometer here. Like as you can see, the condenser is sealed here, but it should not be. It should be open, and the thermometer should be placed in a water bath to measure the temperature at which the like what is the temperature of this water bath. So two mistakes. Number one, there's no water jacket or the water inlet and outlet. Like this inner part of a condenser is missing. The second thing, it should not be a sealed condenser. Thermometer should not be like there should be opening for that to vapors to escape. Otherwise, the pressure will be too high. It might explode. Then draw a label diagram of the funnel and the flask used in titration is step 5 and state how this reduce the pressure is achieved. So how step 5 is done? In step 5, we carry out a filtration under a reduced pressure. So that is the Buchner funnel. Because what is the advantage of filtration under a reduced pressure? So it will produce like filter quickly and it will produce a dry solid. So to draw the Buchner funnel, so we have filter paper is there. This is a filter paper placed here. And this is inside a conical flask with a side arm for the conical flask, and that is connected to a pump. When we reduce the pressure, the atmospheric pressure will be high, so it will force the liquid to flow through the filter paper. Usually, Otherwise, the filtration is a slow process. So this increase the rate of filtration and produce a dry solid. Then how to achieve a reduced pressure by connecting a pump, you can mention. We reduce the pressure. In C1, structure of aspirin is there. The mass spectrum is suggests the molecular formula for fragment which produce this peak. So what like example in a mass spectrometer, when it will lose any molecule, this will result in a formation of different fragments. So if we break down, as we have 92 here, so the overall molecule with oxygen, because like if we have this part, 1, 2, 3, 4, 5, 6 carbon and oxygen, and this one is not there, these two are lost. So it will be C4H4, C6H4 NO. So carbon will be 12 multiplied by 6 plus hydrogen is 4 plus oxygen 16. So 72 and 20, so that will be 92. So this is like when it is lost, this one and this part here, and it will have like 1, 2, 3, 4 hydrogens are there. Like each of them have a hydrogen. 1, 2, 3, 4 hydrogen, and we're left with this one. So as a result, it will produce a peak at 92. High resolution NMR, a nuclear magnetic resonance of aspirin, include two singlet. Singlet means, like example, when the neighbors are not having any carbon and not having any hydrogen, then it will be a singlet. One of the formula below shows a structure of aspirin. Circle the atom, produce singlet peak. How we identify which one will produce a singlet? So we have to check the neighbors. Then like if the one carbon which is not having any hydrogen, that will result in a formation of a singlet. So if this is OH, if you check the neighbor of this OH, there is no, because the splitting pattern is n plus 1, where n is the number of the neighbor hydrogen. So neighbor does not have any hydrogen, so 0 plus 1, so it will give a singlet. So this OH will give a singlet. When we check this one, neighbor, this is not having, but the other neighbor is having a hydrogen. So this won't be a singlet. And same way, if we check this one, this won't be a singlet because the neighbors are have singlet means that the neighbor should not have any hydrogen. Those uh, environment in which the neighbor carbon does not have any hydrogen will result in a singlet. If you check this one, the neighbor is having hydrogen. You have to check both sides. And if you check this one, the neighbor is having hydrogen. One side hydrogen is there. So it will also give a singlet. And when you check this one, like this CH3, the neighbor does not have hydrogen, so this will be singlet. So the two parts which we will circle, that is one is the OH, another one is CH3.